can confirm. The features. And the team of factory worker, I can confirm this. Wouldn't go that far.
No, we have getting levels of knowledge.
No, I'm
Not
not
lying,
lying.
maybe trying
That's why he's from that's what he studied. He managed enough. Oh, yeah. Oh, I know. I know.
And it was like spine day.
So last week, we just started to discuss about the SR motors, switched reluctance motors. So last week wasn't that many of you here, so I just go through really briefly about what we're trying to do, right? So we just show you about a very special motor, which is called SR motor, which is based on the reluctance principle to produce the magnetic torque. We are not using any rotating magnetic flux, or we are not using any DC flux. So in this case, we are mainly using the reluctant force. So by this arrangement, we are able to create a reluctant force that mainly due to the variable reluctance. So this concept, variable reluctance, is to generate the force. So we also call this motor called the variable reluctance motor, or because we're now using power electronic to switch it. So that's why we also call this the switched reluctance motor. So the motor has not been used extensively in the past, mainly because there wasn't any power electronic in the past. If you see other two motors, like the DC motor or industrial motor, they can be naturally powered up by DC source or AC sinusoidal source. So that's why they've been using for more than 100 years. But for variable reluctance or switched reluctance motor, they cannot be energized by purely DC or AC. We do need to use power electronic to do the jobs. So here will be some configuration. You can see that basically the SR motor consists of two substance. One will be the inner rotor, which is built basically without any winding, purely with silicon iron. The outer is usually the stator with some winding between the window here, between the slot here. So the good thing of this motor will be contactless. There won't be any connection from the wire, input power wire, to all the winding there. So that is to say all the commutator and carbon brush disappear from the system. So here will be showing the geometrical simple structure, which you can see that the winding will be used winding on the slot in here, and then inner will be the rotor, which is going to rotate by the reluctant force. So here will be another configuration, which you can see that we put it inside out. So that's to say the winding put it more in the inside, and outer will be the rotor. So this more look like application for the in-wheel motor. So that means inner, this will be connected to the motor shaft, and the wiring, the power will be connected to the wire through the motor shaft. Outer will be rubber wheel connected to the wheel. So there will be different kind of the configuration. Like in here, usually we configure this SR motor to become two number. So the first one is the stator. Second one is the rotor. How many pole in the stator and rotor? Like in this case is 6, 4. So that means we got 6 in the outer side and the 4 in the inner. So you can see that these two numbers are never to be equal. Later on, I will explain to you why they're not going to be equal. And so you can see that every time we energize this kind of the winding, so this will form a reluctant force between them. And then next, when we turn off this winding, we'll turn on other winding, then there's another reluctant force to force this rotation to become an alignment. So that's why one of the reasons we don't have an equal number will be we don't want to lock up the rotor in a particular position. So there's other arrangement 8, 6. So which you can see the outer we got 8 and inner we got 6 of this. And this one more special, we got 8, 10. Outer we got 8 of the stator, inner we got 10. But usually you can see that these two numbers never to be equal. They usually will be even number because they represent the number of the pole. So of course the number of pole must be even number. So the lock up means the rotor will stay in particular stator position alignment without any capability to rotation. That means the torque will be equal to 0 at that particular position. One of the things we're going to show you will be when under the 100% alignment, that means like in this position, when the stator and rotor in alignment, so the force or the torque energized by this reluctance will equal to 0. So that's to say if they're all equal number, they all energize in a particular alignment position without any torque produced, so there won't be any rotation at all. So this kind we call that the pole lock up. So that is the reason we always try to make these two numbers to be not equal. At least there will be at least one pole pair will not in alignment, then we can produce the rotational torque. So here will be some kind of the illustration to show you. Here we got 4 stator pole and 4 rotor pole. They do have a chance that they align to each other. So in this case, there won't be any torque produced by any one of them. Of course, they will have a chance they are not aligned, but they do have a good chance they will align anyway. So that means by using this arrangement, we are not able to start the motor in all the time. We may need to have kickstart. Or sometime in some rotation, they may start in certain position. But however, if they're not equal, one example will be 8 and 6 poles. You can see that. So every 3 of the rotor pole, there will be one alignment. The rest of them have no alignment. So under alignment, there won't be any rotational torque. However, for the other two, we do have. So that means we have a good chance that if this doesn't work, we energize the next one, and the next one, there must be a chance we can rotate the rotor. So here we show you different kind of the arrangement. So this one of the simple motor and called this. Anybody can tell me what kind of the arrangement stator to pole, stator to rotor number? Yeah. Yeah, 6/4, right? This is a 6/4. So you can see that for this 6/4 motor. So for instance, we have alignment here. Next thing, we turn off this winding. If there's a winding, if we turn off this one, and then we start to energize this pole pair, and then this got to be rotate to here in order to complete the rotation. It looks like this have the first line will go through them. So this first line try to shorten the first line or try to pass through in the shortest path. So in this case, we can force the rotor to rotate to have this alignment. So that's how basically the operation like. So this is also a figure I showed you last week, how we start the rotation. So one thing at home, you can start to look into that. When we excite the stator, if in clockwise, then the rotor will rotate in anti-clockwise. So later on, you can figure out how to do that, or you can check my YouTube channel to see how they look like. So basically, you can see that when I energize this one, so this have this rotation. And then if you energize this one, then this will continue to have this rotation. So that step by step, we can able to energize them in such a way, run the stator if clockwise, the rotor will be anti-clockwise. So that's quite special. So that's to say we can also use this method to control the direction of rotation. Yes?
Can you explain how reluctance is used to apply torque on the rotor? Because I think it's not really following the.
Can you observe how the rotation looks like here?
I see
You can see that here, there's a little bit of the spark here.
Yeah.
They're not actually spark in how we energize the corresponding winding. For instance, if I try to energize these two, because these are pole pair, we energize them together, so we create a magnetic force, magnetic flux line between them.
Yeah.
So the reluctant force means we want to shorten the magnetic line. So that is to say, what the best way to do will be to rotate anti-clockwise to have alignment. So you can see that if this have a rotation in such a way, then this will become alignment. Yeah. So that means the rotor should rotate anti-clockwise. So next, after do that, then we're going to energize this one, this two. Then continuously, then we can see that when we energize this one, the first line tend to go this way. So, and then we try to shorten the magnetic path. So the rotor need to rotate continuously to rotate anti-clockwise to complete the path. So once it start to rotate, then now we can become alignment in such a way.
It's,
Yeah. Do you get that?
It's just like a idea here we have to take for granted, or is there some sort of principle that causes the path of the magnetic field takes to shorten?
So the arrangement here will be very energized one by one. We make sure that we need to monitor the rotor position. We wait for the motor go to certain location, and then we energize the corresponding stator line. So that's also kind of technique. We won't misfire, so we need to monitor them. We need to sense the motor position. All this kind of SR motor, we do need to sense the motor position so that we won't misfire. Okay. Yeah. So it's quite interesting. You can work out this diagram to see how we rotate the rotor. You can also change the sequence to have any sequence to rotate in another direction. So here will be other typical example for the stator to rotor arrangement. For instance, this one, obviously you can two motor, this of course it's an X6, right? And so on. You can also work out 6-4 is really common. And also they got more number. Obviously, if you got more high number of the stator pole and rotor pole, then the torque ripple can be much lower because you can overlap them much clearly. And for large number, you may not able to join all the different torque from different phases properly. And one thing I also ask you probably in the homework 5 will be lamination. We can see that the winding will go in such a way that the magnetic flux will then go to penetrate in this direction. Later on, you can work out the eddy current will tend to flow through the iron core. So that's iron core. So that is to say, if we put the lamination as such, then the eddy current is not going to pass through all the iron. In this case, we can reduce the eddy current losses. So that's why I can observe that from this joint, all the lamination in here, right? In this. So the lamination will not put in this direction, but all in this direction, mainly to stop the eddy current flowing through the silicon iron. You can use your right-hand rule or lens rule to work out what is the direction for the eddy current. So I do have one of the homework asked you to sketch the lamination. So here will be another example to show you a 12-8 SR motor. So you can see that all this will be in a kind of the pole pair. We energize them to have the flux to go through them. So you can see this structure, the geometry or the configuration for SR motor are quite simple and easy to construct. For example, here will be the winding. We can put the winding into a former. So we put the winding here. So former is just a plastic. You can hold all the winding. It's a square stuff. And then after we do the winding, we can insert into here to complete the configuration construction. So you can see that SR motor are very simple and easy to construct. So we also discussed about the inductance. So when the alignment happens between the stator and rotor, the inductance must be highest. So you can see that here, when the stator and rotor align, then the air gap between them will be much less. But when they're not aligned, then the air gap between them will be much larger. Obviously, you can see that they affect the inductance. So that's to say, if you try to plot the inductance against the rotor angle, you can see that under alignment here, the inductance must be largest. And then when we have no alignment, the inductance will be lowest. So between them will be more look like a linear proportion. Of course, in practical SR motor, they may not be 100% linear, but they may be curved in such a way. But however, in the pure analysis, we can assume them will be linear, easier for our calculation. Then we also introduce you to a term called the first linkage, L, which is equal, the inductance equal to lambda, the first linkage divided by the current. So we're going to use this one to estimate about the co-energy of the system. So we do introduce to you a new term called the co-energy, which is more look like the energy stored in the inductance of the motor. So the co-energy actually will be a method we usually use in SR motor, how we estimate about the torque. The co-energy actually is one of the new good method we try to estimate the torque. So when we plot the first linkage against the current, we can see that they are not linear. Automatic property, they seldom be linear, they more look like non-linear. But we do observe there's a term when we integrate the first linkage against current, so that is the area enclosed in here, that's the co-energy. So later we'll show you the co-energy actually more look like how we're working on a mechanical spring. So the spring is more look like energy we store in the inductor. By rotate the rotor, we just look like we stretch the spring in order to modify the energy stored there. But more importantly, you can see that later on we show you the torque produced by the motor is equal to this change of co-energy against the angle. So which is to say, if we do the formulation for the co-energy is equal to our energy stored in the inductor of the motor, then when we differentiate it, then we eventually can get up to one of the really important formulation, which equal half I squared dl d theta. So that means this term is how we change the inductance, which more look like the slope in here. Importantly, you can see that when the slope is positive, the torque will become positive. When the slope is negative, then of course, then the torque will become negative. So that means you can see that we are control the torque direction using the slope of the inductance rather than the current. The current become I squared. That means no matter the current is go inside the winding, come out from the winding, then that doesn't change the torque direction. So that is to say from this curve, you can see that. So this is when the stator and rotor in alignment. So when the rotor try to rotate approach to the alignment, then the torque is positive. So when the rotor try to away from the alignment, the torque becomes negative. But of course, we don't want the motor will be positive and negative being cancelled out. So one thing we can do will be we can inject the current. We can put the current in here. So whenever we want positive torque, we will allow the current flow through the winding. When the rotor try to go away from the alignment, we will stop the current, stop the transistor, apply the current to the stator winding. In this case, you're able to control always become positive. So that's to say, so you can see that under this alignment, when you approach, for example, whenever you rotate approach to here, then we start to have positive. Then in here, we can adjust the current to the winding. So once you finish, then we have no current. Next, we'll do it again. So we can control the transistor to apply the current in a good timing. Then we can able to always produce a good torque control for the motor. So you can see that in here, the important point for the control will be we need to control the timing quite precisely. So that means we turn on at that point, turn on the transistor, apply the current to the winding, and then we try to turn off at here. So that means the so-called the switching angle to control will be one of the important control method for the SR motor. So that's why this kind of the control, we can't do it much before we develop powertronic. Only when we develop powertronic, we know how to control the turn on and turn off angle of the motors. So that means we need to develop a constant torque control. So that is to say the current, no matter positive or negative, we always want the current to become constant. In this case, we can able to control the torque, become constant torque control. If the slope is constant, like in here is constant slope, we can also develop a constant torque control. We can also adjust the torque amount by adjusting the current, because the LD theta used for constant speed will be fixed. We can't change it more. So for certain speed, if you want to control the torque, what we can do is control the current. So we can have another current profile to control the current. So that means if we're able to have current like that, then we can able to control. Of course, in this case, we need to control it more properly. That means we only allow this current to go to a particular this region property. And then in here, we to stop this current. And then in here, this amount of current, we will channel to other phases. So this will show you the current at what we're trying to do for the overall DC input current. But however, we need to divide the current in suitable location to individual winding in order to produce the torque control. So another thing we need to look into about of course, the arrangement between the stator pole and the rotor pole. And then we also introduce you a term called the phases. So some people would like to ask me, will the number of phases you always equal to the stator pole pair? For instance, we got 6, 4, then does that mean we have going to use 3 phases? So right now in this motor, for example, we have A, B, C, D. So in theory, we have 4 sets of the winding. Each winding will connect to their transistor. So perhaps I can show you how they look like for the transistor connection. So here will be how we connect the winding to each of the transistors. So that means if any one of phase we want current to pass through them, then we turn on these 2 transistors to energize the winding. And then after next motor rotation, next phase, we turn on another set of winding and so on. If you want to reverse the phase sequence, reverse the direction, so we turn on this one and then turn on this one, and that will reverse method. In this case, you can control the rotor rotational direction and also vice versa. And then, so this A, B, C, D look like to us, we got, say, 4 stator pole pair. That means 8, 6, right? So do you think, so this we call it, say, 4 phases or 4 pole pair? So that's how we can imagine how it look like. But do you think that would be one of the ways we can define the correlation between the number of phases and the stator pole pair? For simple motor, we try to do that. But however, there will be a high number of the stator pole pair. We don't do that. So the one simple correlation I want to show you now will be the number of stator pole actually must be even number, right? And also relate to the MK. So of course, M will be equal to the number of phases. So usually will be K number will be equal to 1. So that means, for example, like just now we got X6 motor, then this is equal to 4 stator pole pair, right? Pole pair. So that means the number of phases will more look like equal to 4, right? But of course, there's some case we will have more number of the stator poles. So that means sometimes one phase current will attach to different stator pole. Later on, we'll show you what the configuration look like. But for simple one, most common one will equal to 1 anyway. So for instance, for 6/4 and X6, now in here, this one will be the X6. So we have one phase into here, and B phase, and C phase, and D phase. So they're commonly understandable, same as the circuit I showed you just now. So that means for this kind of the 6/4, X6, we usually will be 3 phase and 4 phases. So that's how we commonly arrange them. and there will be high number like the stator and pole. We got 10 and 8, so number of phase will be equal to 5. But there will be something called 12 to 8. So that means 12 stator and 8 motor pole. So actually, in this case, if we can consider them as a multiple of 6-4. So actually, this motor same as a 6-4 motor, but we double the number in the stator, and then every time we can use 3 phase, each phase to energize two winding pair. Yes. So in this case, then the K in here will be K equal to 2. Do you get my point? Yeah. So this we use for 3 phase, 4 phase, 5 phase, but this one each IGBT or inverter phase will connect to 2 sets of the winding. So that's how we're going to energize this kind of the high number of the stator pole and motor pole. But for simple motor, we use series. One phase will connect to 1 stator poles. Another concept we'd like to show you will be the stroke angle. The stroke angle is to see every time we energize them from alignment to the next phase, there will be rotation of the rotor. So how much angle of rotation is the rotor? We can actually calculate. So we do have a formulation to calculate will be happen to be 360 degrees divided by the stator pole and also the number of phases. So later on, let's see what that means. For instance, now we have alignment between AA. And the next thing to do, if we want to have a rotation for the rotor in clockwise position, we'll energize this first. And then next, we'll energize this too in the second. So once we do that, originally in that alignment, so this will start to rotate to here. So you can see that how much movement it will be. So from here, we can see that will be equal to this angle of rotation. So that means 360 divided by 4 minus this angle from the stator, 360 divided by 6. So every time when we change the excitation from A dash to B dash, then the rotation will be 90 degree minus 60 degree. So that will become 30 degree. So this angle 30 degree is equal to our stroke angle. So every time we energize, when we change from one phase excitation to another phase of excitation, that is how much angle being rotated. So that's purely just geometrical calculation. So that means for many motors, we do have prefer to have a smaller stroke angle. So in this case, we usually see that the top ripple will be lower because every time we only adjust a small top angle. If the stroke is large, like the 4-2 machine, then in this case, the top ripple must be really large. So let's consider another case for X6. Then you can see that every time, so alignment is here, then the rotor, so of course this angle is equal to 60 degrees, 360 over 6. And every time this, when we rotate, then you rotate to the B location, so this angle are equal to 360 divided by 8, right? So it becomes 45. So every time for this X6 machine, the stroke angle will therefore equal to 15. So that means this motor actually we got less stroke angle compared to this one, 30. Then the top ripple for X6 machine must be better. Usually will be better. Up to this point, any questions? That's a simple, very simple geometry. Yes?
Is inductance in magnetic circuits like more than just like a property of the coil around the core?
It's much more than that.
That's why it changes with angle.
Now, when you put winding here, purely inductance here, you need to, as you know, inductance, we need also need to consider the magnetic part. I think you do remember a long time ago when we discussed about inductance. The formulation of inductance equal to mu naught, mu r. I think it's A over L, something like that, yeah. So that means mu naught is the 4 pi 10 to the power minus 7. Mu r is the material, can be 1,000, 2,000, 3,000. Area is this area. L is the magnetic path. So the longer the magnetic path, then that means the lower the inductance. So you can see that when we have alignment here, so all the path will become much shorter. Yeah. Here will be much longer. We talk much lower in inductance. So that's why I can see the inductance profile change. Of course, this inductance will have few components. One is the iron inductance, air gap inductance. I think we did show you a formulation when we have air gap, how the inductance look like, right? Yeah. So that means you to all this inductance motor we do in the total inductance have two components from the iron and also from the air gap.
Yeah.
But anyway, you need to shorten the inductance. So this is why the reluctant force can force the motor to rotate as you shorten the air. So you can see that every time when we energize them, then we do can calculate how much angle being moved. So that's how we so-called the stroke angle. So we do have another calculation for 12.8. So again, we can see that alignment in here, then this movement here, then we can calculate how much this angle. Again, we can see that. So the rotor, we got 8 of them, so the rotation would 45 minus this angle 30, then we got 15. So very straightforward, we are able to calculate. So after that, I done some summary of all the stroke angle, which you can see all the different machine, how the stroke angle look like. So that's a simply go through all the machine to see how they look like, right? So you can see that usually for the number are large, like in here, we do have more number, lower stroke angle. And also when the number of phases are large, the stroke angle would be lower. So there's some parameter you need to understand about SR motor. So stroke angle, and also that's one of the key parameters for the SR motor. And also you need to know about the arrangement between the stator and rotor ratio. So that to summarize, you can see that the torque ripple is something we are not quite, we can see there's a lot of favorable component for SR motor. You see for all the other DC motor or industrial motor, the torque ripple actually is much lower than this SR motor. So when we calculate the industrial motor, do you remember what formulation we calculate torque ripple? Actually, the current are really much sinusoidal. Because when we apply any sine wave to the industrial motor, the current just pass through the inductor inside the motor. There's all pure sinusoidal. So the torque ripple are quite low for industrial motor. And then when we go to the brushless DC motor, the torque ripple are actually equal to the current ripple for the IA, armature current. I think you did remember the tutorial like that. So we try to use high frequency, we can therefore reduce the current ripple. The torque ripple for brushless DC motor also really low. But here we can see that the torque ripple are controlled by a number of issues here. This is also one of the disadvantage or drawback for this motor. For instance, you can see here, every time only this region control the torque, we need to stop this current, stop this torque, and then once we pass through here, then we go to the next phase. So probably next phase will be energized. So how to overlap each of phase properly? That will be one of the issue. Each phase properly that will be have the stroke angle. So the stroke angle usually try to become smaller so that the overlapping can become more precise. So that all the issue here will make this SR motor have a torque ripple issue, which one of the key drawback for this motor. So that means the top ripple is one of the most serious issue for this motor because mainly due to the commutation. When we change from one phase to other phase, then the commutation will be an issue. We need to monitor the turn on angle and turn off angle properly so that we won't misfire the transistor. And usually the small stroke angle, we can able to reduce the top ripple. But however, small stroke angle, that means we usually have a more frequency to fire the transistor. But however, and then the top ripple usually will be much higher frequency. So the small stroke angle means higher frequency of the ripple. And then in this case, this can be easily filtered by the mechanical inertia. You can see that although we not top ripple, but the high frequency and the motor inertia is really large animal, so which more look like a high inertia. So all these top ripple can automatically filter by the inertia. The motor inertia is so large, so you won't have any ripple movement for the shaft. So that's how we think we like to have a smaller stroke angle. For the control as well, as I mentioned, the turn on and turn off angle is some issue we need to look into because we need to turn on, turn off quite precisely. Especially when the stroke angle is small, so that means the turn on and turn off angle also become really much more precise. Because every little movement, like some of them 90 degrees, within 90 degrees, you should turn on and turn off. And then we go to next phase, turn on, turn off. So there's a lot of work there. So that means the precise how to control them is not a simple issue too. And small stroke angle usually mean more number of poles. So in this case, the window area, so you can to put the copper is also another issue. You can see that so this the window area we put the copper. So when the number of the phases increase, so this area usually will become less area. So that means we don't have that much location to put the copper. So the copper resistance can therefore become higher. We got more power losses. So that's another issue we need to consider for the stroke angle. All right, any questions? They are quite common and straightforward comment. So now we go to the part 2 of SR motor in the second part of the looks. So we like to start to look into the modeling of the SR motor. So modern SR motor very much similar to what we did before for the DC motor. And the method we use are quite different from the induction motor. For induction motor, we did not use that detail of modeling. But for SR motor, the model basically are inductor equation. So firstly, we can see that the voltage applied to the winding, we got the resistive loss Ri, which is a typical voltage drop on the winding, plus the first linkage. When we define the first linkage become the EMF, it can be induced by the winding. So the voltage equation will be equal to Ri d lambda dt. So the first linkage actually relate to the inductance. The inductance is related to the water angle, change with water angle, and also could change with the current. So that means when we differentiate this one, then we have to use the train rule to see that the lambda dt will be equal to a portion vary with the current and also vary with the water angle. So that means the complete equation for the voltage of the motor will be like that. So you can see, we try to energize what it is. And then you can see that that's the IDT. So these are actually our inductance term. The lambda, the I is the inductance L. And then the next term, the theta, the T is the omega, this motor speed. So this more look like the back EMF. You see our back EMF is a constant K omega, right? I think for the DC motor, if you can relate that, if you try to be similar to our K phi omega is the back EMF. So that means that's more look like back EMF. this more look like the voltage LDI dt, more look like the voltage developed by the inductor. So that's why later on then we can therefore move on to this configuration. So lambda, actually, the definition for lambda is equal to Li. So that's the basic definition for lambda. So that's why I can see that we now can, with d theta dt is the omega, this the speed of the motor, and then I in here. So in here, if we assume the current is not changing with the angle theta, that means just now when we do that, we always, when we control the motor, we try to use a constant current in this region when we change the inductor. So if we do that, then we can simplify the equation further. We can therefore put the I in the front as a constant, almost like dl d theta. So that's more look like the slope of the inductance. So we write them, then we got this final equation. So then voltage equal to Ri, which is voltage drop from the resistor, and also the inductance profile, inductance dl di dt, which is the voltage induced by the inductor of the winding, plus this term more look like the back EMF. So this back EMF are related to the motor speed, relate to the current, and relate to the profile of the inductance. So from this equation, anybody can tell me how that equation relate to what we learned before, like the DC motor and also other type of the motor. For DC motor, we do have this term Ri, right, winding resistance. But for DC motor, we have the back EMF omega and some constant. But now then we got two different terms as compared to our DC motor. So anybody can tell me any more observation, anything can comment on this equation? So when this motor, when we start the motor, this motor, let's take, for this motor, then we have this term, right? So when we going to start the motor from standstill, then the back EMF will equal to 0, right? That will equal to 0. Then similarly in here, when we start the motor, then the back EMF can also become small, right? Even though we got current there, even though we got the LD theta. So there will be some common point between a simple DC motor and the SR motor. But in here, we do have a term related to energy storage in the SR motor too. So that is to say the three term we examine here, this is the inductance voltage drop. So if we got a large change of the current, then the inductance voltage drop will be large. One thing you can see here, if we're going to use a control method, control constant current, then voltage drop on that inductor will be negligible. We don't do very too much about it. Of course, when we change in the current from certain one torque to another torque, then the IDT will be large. But for constant current mode control, if you want to control the torque to be constant or using constant current to do that, we can therefore reduce this amount of the voltage drop. So if this is become lower, and then this certain fixed parameter, input voltage, of course, will be fixed depending on the DC voltage connected to the inverter, then we can able to maximize the amount of the back EMF in the induction mode, in this particular SR motor. So the back EMF term here, we determine the motor maximum speed that can given on a given supply voltage. Usually for motor, we want to have given DC voltage. And then we want to add using the voltage applied to control the speed of the motor. Like this motor, like the DC motor as well, we got V in equal to, right? Ri plus K5 omega. So that's for DC motor. For given voltage, because this will relatively fixed, then the motor speed really much controlled by the input voltage. Of course, we can use field weakening. We can therefore increase this one. So that's how the limitation for the speed for the DC motor. We can only increase the DC motor speed by using higher input voltage. So, but in this equation as well, when this input voltage being fixed, the voltage drop also being fixed by the winding resistance. And then if we can use constant current, we can therefore reduce the voltage drop on the inductor. And then now then, if we want to increase the speed, what we need to do is trying to work something on these two components. So the L theta and also I, we can add to see what we can do to increase the motor speed. So there's some of the design criteria we need to look into. So obviously you can see that there's a lot of the non-linear term for the motor. So DC motor is really much linear. Everything will be linear, very easy to control. But for this SR motor are not the non-linear term, including this is non-linear, although it's in theory they are linear slope, but in practical case they may not be purely linear. And then we also have the IDT term as well. So that also make all the motor become quite non-linear. So the control of this motor will become more complicated. So that's one of the reasons this motor is not widely being adapted, because the control need a lot of the work. So let's see a simple tutorial so that we understand the basic operation for the motor. So we see if we try to regulate the current at 15 amp, that means current become constant. So the speed is 400 radian per second, and the inductance profile will be the LD theta 0.08 Henry per radian, and then so when we do the conductive calculation, because the current is controlled at constant 15 amp, so the ID theta becomes 0. So in this case, we don't need to consider this term, right? We don't need to consider this term. Let's see how we can get the voltage is Ri I omega dL d theta. So we have 15 times 0.2 ohm, then we got 15, and then we got speed here, we got the LD, d theta. So that the input voltage becomes 483 volt. So that means in here you can see that in order to ensure the motor can able to run at 400 radian per second, the input voltage at least to be 483 volt. At least, if you want to have better control, then we need to look into how we control the input voltage. So that is simple tutorial. So at the correlation between the input voltage and also the motor speed when the inductance profile is given. For any motor, the dL d theta is how the inductance should look like. So when we construct a motor, the inductance profile already given. So inductance profile which is that characteristic. So this is the characteristic we are talking about for L over d theta. So this is important profile. For any industrial for any SR motor, we usually need to determine this profile, which is major characteristic for a motor. Then the motor given, we usually need to measure it to rotate the motor with motor angle and measure its inductance. Then we can know these parameters. So that's how we control the first step. We try to control the induction motor. So next thing to see if able to derive the torque equation. So we do have a standard equation like that. I think we do talk about in the last few pages. We can divide the torque using the co-energy, right? But the concept of co-energy is quite complicated. Let's try to use the voltage equation to see if able to derive the torque equation. I think, have you reviewed this page before you come to the lecture? Right. Let's go through that too. together, right? So the way I divide the torque equation, firstly, to use the power. When we have the voltage, then we multiply the left and right side by the current, we are able to get the power. So firstly, we get a power equation. Input power equal to this one, and all multiplied by I current. So that's first thing we like to do. Once we know the power, if we assume the 100% efficiency, we can know the output power equal to torque multiplied by omega. And anyway, so later on we can relate all this into torque omega, then we're able to work out the torque. So that's basically most of motor, we try to use this idealized characteristic to work out the torque. So that's why we start from the torque equation first. And then for the power, then now that's the equation we try to use. So firstly, we know that energy stored in inductor is half Li squared. So which energy stored in here? So the rate of change of the energy stored, then when that's the power for the stored energy, then we differentiate this one, then we can get to that one. Why we do that? Because the inductance actually could change with the time. Because changing the angle will change at the time. So we do need a term like that. The current can also be changed with the time too. Because when we work out the torque, we cannot always assume the current will be constant. It can be for any current. So that's why the way of change the energy, we have this formulation now. Then you can see that the inductance here, we now talking about rotation motor. So we change them into the theta using the chain rule. So we got d theta, d omega. So the rate of change of energy will therefore become this. So d theta, dt will become our omega here. So now we have this equivalent for power. So now then we go to next equation. So the mechanical power is equal to input power minus 2 power. One is the power losses from the resistor. Another one will be from the energy stored. So that means we will have original formulation minus the resistive losses and minus the power of the stored energy. Then we consider a few terms and we cancel out. Then eventually get to this term will now become this term. So that means mechanical power will therefore equal to this one. So this is the same formulation we get from last week when we differentiate the core energy. So that can verify what we have done. We can have, using the voltage equation, we can derive torque equation. And then last week we also make use of core energy. You can also divide the torque equation. They are actually is the same formulation. So that means the core energy is the energy related to our motor torque. So this also a really important formulation, how we understand, how we control the SR motor. So that's again, I square of the current and the inductance profile. So do remember this formulation. So you can see that it proportional I square. For other motor, it usually proportional to the current like the DC motor, but here will be I square. That means will be again independent of the current direction. Any comment up to this point? So let's look at the more detail about the motor operation. The SR motor just like a number of the inductor putting together into the stator slot. So let's see how the magnetic flux look like. Actually, when we design a motor, we usually tend to understand more about how the magnetic flux going on in the motor. For a good motor, we tend to reduce the magnetic path go through the air or go to the outer rim. So in this case, if we can able to shorten the magnetic path, we usually have high efficiency, high performance of the motor. And then you can see that the magnetic path usually try to look for the least inductance path. That means lowest magnetic resistance. So when we have winding, then the magnetic flux will try to pass through them. So if we energize these two, right? If we try to energize these two, there's a number of ways the magnetic path can go through them. They're not necessary to go to the outer rim. It may go to some adjacent rim. So you can see that in here. In theory, this magnetic path can therefore go through in here. Go through in here, right? And then you can see that when we do so this simulation, we are using a finite element to look in the magnetic path. You see, it's difficult, impossible for us to measure the magnetic path inside the iron. So that means today, everybody, when we try to understand the motor operation, we'll use finite element, FEM, to do that. Finite element analysis is really standard method. We try to analyze all the magnetic flux inside the magnetic circuitry. Then in here, it's impossible for us to measure how the magnetic path look like, but we can use finite elements, a really well-developed method. We can do that. And so you can see that the magnetic path we can go through here. One thing you can see here would be we don't need to have magnetic path to go through the middle, because there's a sufficient path for it to go around the center. So somehow for this motor, we can able to have an empty area in the center, because that may not be doing reduction of the magnetic path. And so that's why for many motor, center will be empty. We just allow the shaft to go through them. And then from this, you can see that some of the field may also go through this path too, right? So that means when we start in the beginning, before you approach the alignment, you can also go through this path. Even though we have not energized this winding, some of the magnetic path will go through in here. Of course, most of the magnetic path will go through in this one. And then you can return back to here. So that's to say, in theory, although we say the magnetic path will always go through here, but you can also observe from the finite element analysis, the path can also go through the adjacent magnetic path. But of course, which one will be the first? Then the one go through the center will be the major one. We do see a little bit, because this one will disappear really quickly. Once the alignment appear in here, then the flux will quickly all focus on the major magnetic path. This path will going to broken really quickly. So that means you can see the main magnetic path. We may go through the magnetic rod. Then you go through. When we energize each one of the magnetic pole, you go to the corresponding air gap, and then go through the magnetic pole, and then complete the loop in the magnetic core. So that's how they look like. So that means when energize them, then go through in here and complete the magnetic loop. So that's mainly about how the magnetic path shall look like. So that's one of the comments is when some people design the rotor, they try to make the rotor center become hollow. The thing is, for geometrical point of view, we only have sufficient magnetic path or sufficient magnetic area will be good enough for reduction for the reluctance. So that means we don't really need to have a solid center. So in this case, we can therefore make sure that when we have sufficient direct path go through between the stator and rotor, and this path will also go through the outer circumference. Like what I showed you just now, the path will also go through the circumference. And then by using hollow, we can therefore save the material because all the magnetic core are important. We also create a lightweight because as SRM, we only need all the rotor pole. So the one in center is not doing any real job. So we can also use this method to reduce the inertia for the rotor, make the rotor lighter. So that's why this motor can be the fast, the high speed. So that is to say, we can reduce the speed, reduce the cost, and improve the performance because the rotor will be mechanically more robust by reduce the magnetic components. So, and more importantly, will be we understand briefly about the geometry. Next thing is understand how the operation is. So you can see that this motor driver is somehow will be different from the conventional induction motor driver. I think you've seen the induction motor driver. Do you remember how the induction motor driver compared to this one? Anybody can tell me? Do you remember how we drive the induction motor? Three-phase induction motor? This is a four-phase anyway, but three-phase, if there's a three-phase, you just listen for this one, right? But for induction motor, can you remember the difference between the two circuits? Tell me what an induction motor look like for the driver. Can you sketch it? Try to sketch the induction motor driver first. After done that, then compare your joint with this circuitry. What are the differences? I think we did go through the induction motor driver. For somebody if they done some inverter in the past, like the solar DC pump, you should also know how the configuration for induction motor, right? How does it look like? Sketch it and then compare with this one. There's a major difference for the configuration. They look quite the same, but they're quite different between these two. Once you catch the induction motor driver, then you understand what I mean. Or you can get back your looks, how the induction motor looks like. Your actual state of instead of one is the diode is where hi, the diode. That's the thing I like to talk to you. You see a conventional induction motor, usually are three-phase. Then you can see that we have 6 transistors. Each transistor has its anti-parallel diode in here, right? I think that's a typical configuration for induction motor. They are all standard one. But you can see that the winding or the output connection to the induction motor, make sure that these two transistors are joined together, connect together. But if you compare with this SR motor driver, the winding for the stator between the two IGBT. Why is that? Anybody can tell me what are the difference of why we need to do it differently? They are all energizing the winding. Why we need to do that? Any comment, observation? The number of components actually are the same, 2 transistors and 2 diodes for each phase. And then you want to
Let's say that the not polarity, but like the rotor is different in both cases. In the induction motor, it's a PN, and so kind of has defined magnetic moment vector. And in the SRM case, you have just what you would call it. It's just a piece of metal, right? And so as you kind of like rotate it, or as you like transition between poles, you kind of have like a slight. It's not like there's a set moment vector for the rotor in SRM.
You see, for both induction and SR motor, we only energize the stator winding. For induction motor, we only stator winding. The motor winding, we don't care. Yeah, the induction principle will take care of it. So every time in here, when we energize them, each one will be displayed by 120 degrees. So we always have power to all 3 windings. Sinusoidally, displayed by 120. So they all are switching continuously. Of course, actually that we are using PWM, but they actually are switching continuously, power by 120 degrees for each of the phase. But here will be different. As I mentioned before, for this kind of arrangement, each phase are also independent winding. Of course, in phase A, we got 2 windings, A and B delta. 2 windings connected in series, but basically one set of 1 winding. So when energize them, you do remember that each time we only energize 1 phase. The other phase will disable. We need to wait until the rotor will rotate to that particular phase. Nearby, we start to energize them. So we only energize 1 by 1. We don't energize them together. For this one, we all energize them together, but for this one, we energize them separately, independently. We seldom, never will connect, will energize them together. So that's why if you do that, if you energize A phase, then we need to provide both the voltage injecting and return path. For this winding, we do a return path for other phase. For instance, if we energize this phase, so this current will go to here, you can return to here, or you can also return to here. So that means we always have a return path for any one of the winding. But here is not the case. When we energize the A phase, we need to make sure the A phase winding has its own return path. So that makes the difference. So that means when energize it, make sure that this point and this point do have the something connected to. So that means will be energized in such a way. We cannot only energize 1 terminal of the inductor because they're highly independent. So if you do that, so as I said, you need to monitor the rotor opposed to the before alignment with energize them. So that is the same one. You can see that there's a lot of the stuff here. So for instance, when we start to energize this B phase, so this supposedly will rotate to here. So during that time, this winding and this winding are excited, but A phase will disconnect the power. Low power to all the other phases, only B phase. Or vice versa. So that is to say in here as well. So we energize one of the phases. So we make sure that we connect the DC voltage to this winding. The only thing we can do will be using 2 transistors independently to connect these 2 terminals to the DC. And we also need to ensure that all the other phases are disconnected. So that we need to connect a 2 transistors for each of the phase, turn off, to make sure that B, C, D are not connected to the DC source. So that's how we make them highly independent from each other. We can't do this circuitry because they all connected somewhere in somehow. But this one we can ensure the A, B, C, D coil are independently controlled. This first point we need to do that. So that's why we need to use two separate IGBT to do job. That's first point. Second point will be the diode. Anybody can tell me what's the function for the diode?
Allows current to flow one way.
Yes. And for this particular application, why we put the diode so string quite different from there. You see, for this arrangement, the diode are in anti-parallel to the IGBT. Anti-parallel, that means opposite direction in parallel. But this one, originally the diode should be right in here. What was the point to put it in this funny location? You say something good, but I want more than that. Yeah. Anybody can give me a hand? What happened? This is a really standard circuitry for SR motor. Think about that. What happened here? Why that? What's the function for this diode? What's doing without diode? What happened? It's possible without the diode. Why we do that? Why the location like that? Yeah.
When it switches off, it gives a direction for the current to go because it's like.
Yes, that's what we trying to do. You see, when we turn off the inductor, then we need to go to next phase to do that. Then we turn on the both IGBT simultaneously turn off. But the energy inside here does not disappear. So that means current, the current is flowing in here. Then when it is off, this current will be therefore return to here, like that. Return back to the DC source naturally, so that we won't have any spark. If we just turn off our inductor, you know that will be high spark. We call DIDT, high DID. When we turn off the current instantly, that means, wow, LDITT in here, the DI will be equal to maybe 1 nanosecond. You can imagine how much voltage you can generate, million of the voltage. They will fall up everything. So that means for this circuitry, we don't need to have a diode put in such a way to allow this current to regenerate back to the DC source to reduce the current naturally. So that's why all the phases are doing in such a way. So that's one of the comments I'd like to ask you again. This kind of the motor driver is not commonly available. This is commonly available. For induction motor, this kind of the 6 transistor inverter arrangement is widely available. You can buy it in very low cost because induction motor has been in the market for more than 100 years. So this is really, really low cost. But this one is non-conventional. You can't find this inverter bridge like that in the market. The market share only 1%, 2%. So that's why this becomes really expensive. Although the number of components is exactly the same, but nobody manufactures this, becomes really expensive. That's why the SR motor is not that common, because we can't find this inverter in the market. Not available. But this one is widely available. So low cost. All the inverter at home for inverter, for motor driver, we're all using this. So that's why really, really low cost, but not for this one. So that's one of the reasons why this SR motor is not that common at the moment, but are more expensive. That's mainly about this kind of the issue. Any other question? No? No. So 15 parts, yes?
The SR motor kind of reminds me of the step move.
Really much close to that. The stepper motor and SR motor are really close to each other. They do a lot of the commonality. If you have time, we try to go through the stepper motor too. But probably we only have 2 weeks left. And you don't have time to go through that. But SR motor and stepper motor are quite similar. For some simple control, we tend to use stepper motor for some simple rotation. But for high power, high current, we tend to take this SR motor because we can able to control the torque in between the stator. So this is something we like to do. Yes.
This produces more heat than that one, right?
Why you say that?
Since they could more MOSFETs, more diodes.
No, the number of diode and transistor exactly the same. You see, if we totally have 6 transistors, 6 diode here, also about say for apple to apple, for 3 phase, then we also have 6 transistors and 6 diode. Yeah. So each phase we have 2 transistors and 2 diode, exactly the number of components. You see, when we energize the phase A, these 2 are being turned on. So when we energize this one, from Newton, this phase, this is to turn on somewhere, either this or this transistor, this to turn on. So the conduction losses are exactly the same. There won't be any difference.
What is the point of the D2 diode? Why do you not just have the D1 diode?
Because when this current needs to return, they'll return half.
Okay, so
Until the half. We'll continue discuss on Wednesday. See you again then.
Yes. Yeah.